So my first slide is to justify the analysis of migmatites and granites, and I put in between granitic gneiss. Probably you people working in India are very familiar with these terms. It's not so obvious in Europe because we have less of these rocks, even though they probably represent 20 to 50% of the outcrop of the surface exposure, but they've been a bit neglected. So I need to justify to study these rocks. And granitic gneiss, it's because I think there's, as I said yesterday, there is a difficulty to make difference between what corresponds to metamorphic rocks and what corresponds to plutonic rocks. And in between, well, if we don't know, put that into granitic gneiss, and that's all the pink. Most of the pink here is granitic gneiss, meaning that we don't know if they are metamorphic, plutonic, and whatever. It's an easy way out. And I don't know if you guys already mapped. At some point when you're mapping, you have your organization of lithological units, and there are rocks that you don't know where to put. You need to find a bin. Granitic gneiss is in an easy bin. And you can put most of the continental rocks into this bin. So, no need to justify, it's very important. And sediments that have been over-studied, I think in Europe, it was natural because it was fairly easy to understand what was recorded in these rocks, in these sediments. Sedimentation that you can see with your own eyes happening today in rivers, on continental margin. You see what's happening, so you can relate to that record in the past that is recorded in rocks. Same for volcanic rocks. But for metamorphic rocks, plutonic rocks, it's more difficult to relate to something that is happening today at the surface, because it's not happening at the surface, it's happening at depth. Morning. But these sediments, they only represent, well, a small cover, a thin cover of a few kilometers at most, if it exists. The rest of the continental crust are these gneisses, migmatites, granites. So that's the most volumic important part. So I think that's very important to consider them in our studies. So what will the structural analysis of migmatites provide? So we'll see a bit later on the difficulty about studying the structures of these rocks. But what we're going to really get out of that is how they behave mechanically, the rheology of partially molten rocks and magmas that will come out of this structural analysis. It's really how they deformed, and then how they deformed tells us how they behaved in terms of mechanics. But then there's also another process which is related, that is recorded in these rocks, is, so migmatites, I should define them now. I'll do that later on, but they are made of a mixture. Migmatite is mixture of rocks. Of a white part that has a quartzo-feldspathic composition, a texture that we interpret nowadays as being representative of a melt that has crystallized, a silicate melt. And the gneissic part, that is the gray part, that has a preferred orientation and a texture that reflects deformation before the presence of the granite. So it's a mixture. And we interpret this mixture as being representing a coexisting melt and solid in the rock at the time they were deforming, so partially molten rock. And as these two phases, the solid and the liquid, were coexisting, well, they could separate from each other, segregate. So the structural analysis of migmatites is going to tell us about melt-solid segregation. It's not a closed system, it's a system that is very complex. And then, what we'll do is we'll jump scale, mostly to more, and looking at what is the impact of partial melting that is recorded in the structures on orogenic evolution, and also on crustal differentiation, because this process of melt-solid segregation is the main process of crustal differentiation. Starting with a homogeneous crust, you end up with a differentiated crust in different layers. More mafic in the lower crust, felsic intermediate in the middle crust, and more granitic and sedimentary aluminous in the upper crust, where surface processes take over the magmatic processes. Okay, well, we move from these ideas that were mostly motivating people to look at the relationship between magmatism and tectonics, and we'll go towards that. The first idea that motivated such studies is, well, maybe the way that, for example, lithospheric thinning would control melting by decompression of the mantle underneath. That's one way to connect tectonics, geodynamics, and magmatism. How tectonics will drive melting and magmatism. Another motivation was to say, okay, in places where magmas are in place, for example here in a pluton, granitic pluton in red, it might correspond to weakness in the crust and localized deformation. So the motivation was here to look at the relationship between magmatism and extension, localization of deformation. So move back a bit into history. So we saw yesterday the debate between Neptunism and Plutonism, with on one side people that thought that all rocks formed by crystallization of minerals in the Earth ocean, so it's a sedimentary origin for all rocks, and Plutonism that said that, well, but there are also magmas that are produced at depth. Good morning. And not all rocks are sedimentary. And much of the debate focused on the origin of granite. You know all granite, huh? But does any one of you has seen a granite crystallizing? No. This is a concept. It's not an observation. Granite, its composition, texture is an observation. Granite being a magmatic rock, crystallized from a magma, that's a concept. Right? Nobody has seen that. This happens at depth. So this debate was very important, and it was natural. Now, we think it's obvious. We take it as a data, but it's really a discussion. So what were the evidences for granite being a magma? Because if we go back to this map, most of the granites are below sediments. So that was the first order observation of Werner and his team, is to see, okay, the granites and gneisses are at the bottom of our stratigraphic sequence. So they represent the first rocks that crystallized in the ocean. That was the logic. So what Hutton added, he said, but look at here in Scotland. Here are the sediments stratified. And the pink stuff is granite. It's not just underneath, it's cross-cutting. So that's the evidence for intrusion of granite into sediments. So in other words, it behaved as a magma that was flowing and cross-cutting the stratified sediments. So with relative chronology, that we know that now, we propose that this happened after deposition of the sediments, so it's not before. It behaves as a weak material, low viscosity. The next evidence was provided by Lyell. He said, but look at what happens to limestones at the contact with granite, with intrusive granite. They are transformed into metamorphic rocks. So granite also add some heat to the host rocks, and that's also one way to propose to argue for a magmatic origin for the granite. But then there was also this debate. Okay, is it all crystallized from a magma, or is it also metasomatic with the action of fluids that would help crystal growth? And this debate went on for the last century. And also then the relationship between granite and migmatites, per migma and ad magma. And it's here a drawing by a geologist, a Reed, that proposed some artistic view of how magma would be produced in migmatites and then feed volcanoes. About 100 years ago, well, some guys reproduced granite in the laboratory. So they managed to melt a rock and then look at what happens when it crystallizes or cools down. Basically playing with the temperature. That's the temperature here, so it doesn't read very well. That's the original figure of Tuttle and Bowen. And Bowen, that's the guy who gives his name to the Bowen series. That all comes from thermodynamics, fed by experimental work. And here, for example, we are in the NaAl Si308, so that's albite. And Kal Si208, that's K-feldspar, orthose system. And so the composition changes in this axis and the temperature changes here. And that's the melt. So that's the solidus, that's the liquidus, sorry. That's the liquidus. It's the line that separates the 100% melt from partially molten rocks. And what this guy showed is if we take a composition of a melt that is here, when it's 100% crystallized, it will give this proportion of these two minerals. But the first crystals to be crystallized will be on this side. And the melt composition, as crystals will crystallize, will evolve along this line. And the last melt drop would have this composition. A composition that is different from the composition of the early melt. So if this melt, this last drop, is separated from the crystals, then it would lead to something that is more potassium rich. And the residue would be more sodium rich. They did the same experiment in 3D, adding SiO2, quartz. And what happens is that, and this point is called the eutectic. Are you all familiar with this, with thermodynamics? Huh? And you can do the same experiments on the other way, by melting. And the first melt will have the eutectic composition. And then the melt will evolve until 100% of melting, and then it will reach the initial composition. So when they did the same analysis with the 3 poles, then they identified that the eutectic point has a composition that is close to the one of granite, halfway between plagioclase, K-feldspar, and quartz. And by making this reasoning about what crystallizes first and what is crystallizing at the end, this explains why K-feldspars are the first to crystallize, and then plagioclase, and then quartz in the interstitial space. So the next debate was about the room problem. If granites are indeed magmas that are coming from the lower crust, well, they represent today huge volumes. And if they were transferred through the crust, which place was it taken? Did the rock go aside? And how did it happen for this huge volume? One solution, so it really led to a diversity of terms, which I'm not going to go through now. But there are different processes that were invoked. disappears, in mass motion of this volume of magma at once, or through dikes, small veins. And what is the link between migmatites and granite? So that would be the in-mass displacement of the full volume of granite. So this space has to be found in 3D in the crust during the transfer. Another elegant solution was to consider that not all of it moved at once, but was transferred through small conduits, small veins. Maybe not only one, but many of them, that would feed a volume of magma that would increase progressively as the melt would go through. In other words, that solves the room problem. That was a smart idea. And then in order to assess these models, and you need also to look at the deformation of the host rock at the place of magma emplacement, and see if the space taken by the magma is consistent with the space that is recorded by shortening in the sediments or in the host rocks. And also the timing. Was the granite also deformed at the time of emplacement, or is it post-deformation, post-structures, or pre-structures? So you need to construct these, so you need to take many measurements of foliation, lineation, and so on, inside the granite, outside the granite, and see how it looks in map view. So these are the general motivation. And now we're going to go into the definitions of migmatites. So the big book on migmatite is Menard, 1968, almost my birth date. And at first, migmatite was defined by Söderholm, a Swedish guy, no wonder. He was living in a craton like you guys, the Scandinavian craton, full of migmatites, so he was inspired by that. And he proposed a mixture of two genetically different constituents. One is intrusive relative to the other. To this group belongs the gneissic granitic rocks, see, gneissic granitic, which show net structure characteristic of incipient melting, frequently blind-ending veins, breccia-like granites with innumerable fragments of more or less completely dissolved older rocks, and finally stripped granites in which the only still preserved parallel structure indicates a faint remnant of the original properties of the rock. A lot of things, huh? A bin, You don't know where to put the rock, try to have a definition that is as wide as possible, then you probably manage to put your rocks into that. And I put in red all the processes that are involved. Intrusion, melting, dissolution, deformation. So lots of processes are invoked in that definition. Very, very complex definition. But in a way, after 40 years of working on migmatites, I see what he meant. Because it's that complexity that he wanted to represent. And a number of words have been also associated to describe migmatites: arterite, agmatite, veinite, phlebite. Looks like you're going to the doctor. Diatexis, anatexis, palingenesis, metatexis, many terms. Again, this reflects the complexity and the difficulty to really understand what is happening. So if you're having trouble with migmatites, that's not a surprise. I also I'm still very puzzled when I go in migmatitic fields. It's very demanding. So these are all the migmatites that Menard described in his book: agmatitic, dictyonitic, shoalen raft, folded, stomatitic, suriatic, schleren, nebulitic. You can always find a friend when you're in the field. I think what is more compelling is this type of definition. And that's the one of Menard. A megascopically composite rock consisting of two or more petrographically different parts, one of which is a country rock, generally in a more or less metamorphic stage. The other, so that's the gneiss, the other is pegmatitic, aplitic, granitic, or generally plutonic in appearance. That's the granitic part. So he added then this threefold definition: leucosome, melanosome, mesosome. Luco is for a white body, the lightest colored part of a migmatite, made of quartz and feldspar, with a magmatic texture. I think that's the key. Melanosome and mesosome is more difficult to really sort out, but it's made of iron magnesium rich minerals, biotite, amphibole, sometimes pyroxene. And the melanosome is usually surrounding the leucosome, and the mesosome is the intermediate between the two. So these are, I think, objective criteria to describe the migmatite. I use these when I describe migmatite in the field. And then he proposed these terms: paleosome, neosome, mobilizate, restite, resistor. And that all refers more to processes. So if I use these words, I use them when I interpret what I observe, not to describe. And that's something very important in the terminology, I think, is what's a very good example here. A terminology should be objective, based on observation criteria. But if the heterogeneity of rock doesn't allow to find easily the criteria to distinguish between rocks, then you end up with a very rich terminology, very complex. And it's not that useful. Let's take, for example, differences between different type of rock, of metamorphic rocks, mica schist and quartzite. We say, okay, 50% of quartz and above, it's quartzite. Below, if it's 50% of mica, it's mica schist. Why 50%, not 45, not, you know? Well, we take an objective criteria, 50%. Does that represent a process, an underlying process? We're not really sure. We probably know that if it's more quartz-rich, the sedimentary protolith was more evolved in terms of maturation and the separation between the different elements. If it's more mica-rich, it was more towards the clay and closer to the source or something like that. You know? So this relates to the process. So in other words, the terminology should help you go to the process, but it should not constrain you to the process. Like paleosome, if you use that in the field, you make an assumption not affected by partial melting. So you make the assumption that the paleosome, which usually in the mind of Menot is the mesosome, was not affected by partial melting. How come? You are there in a few meters, the PT conditions, which are the main parameters that are going to influence melting or not, and the chemical composition are not going to change so much. So there's no reason to keep a rock not affected, and just next to it, a rock that had the same composition, but then melt and solids were segregated. So I think these are risky. So we keep with these ones. But the idea is that from that analysis, then maybe we can assess whether we can propose a composition of a protolith, a rock that was before melting, and then identify which part was crystallized from the melt, and what was not, what was resisting from melting. Maybe some rocks did not have the right composition to melt, so that's resistor. And restite is the residuum after melt solid extraction. So when we look at this structure, very complex. It's no wonder why structural geologists didn't want to play with these rocks. How much of this structure is inherited from metamorphic rock before melting? How much relates to melt-solid segregation? And how much relates to deformation at the time the melt and the crystals were coexisting? These are the main questions we want to address. But before doing that, I'm going to go back into the basics of structural geology, so that we show that because I'm not sure you all had structural geology. You are teaching that, I guess? But not everybody. So the basic. So I think I said it yesterday, but it's very important for me is to distinguish plate kinematics, which is defined by motion of points far from the plate boundaries. So considering that the plates are rigid, not deforming. Plate tectonics doesn't work along plate boundaries because there rocks deform. and the plate is not rigid anymore. That's why geophysicists said, okay, that's the complex zone of arc-like rocks. No? We don't understand. We cannot do plate tectonics in that. Plate tectonics is not about tectonics. It's about rigid motion. Tectonics is about rock deformation. So the name plate tectonics might be confusing. So we consider divergence, convergence, strike slip, plate kinematics. And then tectonics is about crustal deformation. Here the terms that I said yesterday that might be used with different meaning. Extension for a tectonics guy is when the crust is thinned. Compression is when the crust is thickened. And strike slip is when two zones of crust are moving relative to each other in the horizontal horizontal displacement, and usually by simple shear. And in between you have all the cases between compression and strike slip, which is named transpression, and all the cases between strike slip and extension, which is transtension. And that relates, so when you try to relate to plate kinematics, usually compression is related to zones of convergence, extension to zones of divergence. Strike slip is like plates are moving on a horizontal plate, horizontal dimension. And in between, transpression is when the plate is moving relative to each other, but not perpendicular to the plate boundary, but with a slight angle. So it's oblique convergence, oblique divergence. And in between, it's normal divergence, normal convergence. But it's very difficult to retrieve from structural analysis plate kinematics. But you can, if you have the right structural structures. So structural analysis, well, we rely on the final state. What rocks look today, unless you do neotectonics, where you, actually I was sent this last night, a movie that on YouTube, a guy filmed in direct the motion of a longer plate. Impressive, you can see the earthquake and boom. The first time I see that. Check on YouTube, maybe I can send you the link. So we look at the final state. So you guys know what the initial state looked like, because you probably know this type of cakes. Right? But if you didn't know the cake, how come you know it's the final state? It's because you have a mind idea of what was the initial state. And same yesterday, and we discussed that with the limestone. Because you're geologists, you know that the limestones are deposited in horizontal planes. So you know when it's like this, well, it's been folded. But it's not obvious. So that's the initial state. So that's a cheap analog experiment. So we rely on final state. And structural geology is really a geometric analysis of structures with the aim of defining deformation state, reconstruct the deformation history from initial state to final state, and also by looking at the structures, it will allow to quantify pitting conditions of deformations. You don't have the same structures when the rocks are cold and when the rocks are hot. We saw that yesterday with the experimental deformation leading to fracture or to flow. And then, if we're lucky, we can translate this geometric analysis of deformation, shortening, lengthening, in plate motion and or forces causing deformation at the large scale. So the first step is, by looking at structures, identifying the strain ellipsoid, reconstruct that. Where is the stretching direction, the shortening direction, and why is intermediate in between the two. So if you look at the fold like this, you have an idea of where the x direction, maybe the easiest one is to think about shortening direction. You see where it is? Or here? In which dimension the cake was shortened? Horizontal. So if you say shortening, that's not enough. You have to say horizontal shortening. Because if material is preserved, then if it's shortened in one direction, what happens in the other direction? It's lengthening, stretching. So shortening in that direction, in which direction it is stretched? Vertical. You are a structural geologist. Same here. Shortening, horizontal dimension, stretching, vertical, and intermediate, perpendicular to the screen. So that's another confusion not to do. We have seen rocks that have been shortened. Yeah, it doesn't say much. You have to say in which direction. Because if there is deformation and mass conservation, then if it's shortened in one direction, it's stretched in the other one, perpendicular to it, by definition. So the next step is to relate this strain with the stress ellipsoid. The stress is the derivation of a force in one point and corresponds to a vector that we can subdivide in three main axes, sigma 1, sigma 2, and sigma 3. And this stress ellipsoid doesn't have to be parallel to this strain ellipsoid. So that's all the difficulty. And to make it very short, what I do to my students, I take a volunteer, and I say, okay, I'm going to punch you in the face. Usually there's not too many volunteers. But still, I'm just going to do it symbolically. And you don't know, at the time of the hit, when you receive the punch, then you feel the force. But then, just shortly afterwards, you just feel deformation. The force is gone. And you don't know, just by looking at your face that has been punched, if it's been punched direct, how do you call that? Hook or uppercut. If don't know the motion, right? You just look at the final state. Right? In other words, so only when it's direct, that's what we call pure shear, then it's what is the case of coaxiality between stress and strain ellipsoid, then there's not much rotation. But all the others, rotation of the deformation object. So when it's rotating, well, no way to go back to the stress ellipsoid, because there has been a rotation between the deformed object and the initial force that caused this deformation. And usually they understand. Okay? So don't talk to me about stress. Talk about strain. The only case where stress can be retrieved from strain is instantaneous deformation, very small deformation in pure shear. Three conditions that are not met in the deep crust. It's only met in the upper crust. So people are doing fault analysis, that works. And I'm not saying that we never can do that, relating the strain and stress ellipsoid. It works for fault analysis and folds that have not been too much folded, rocks that have not been too much folded. So instantaneous strain, small strain, and pure shear. This I'll skip. So that works on the upper crust. But anything below, where you have a component of non-coaxial deformation, in other words, there is rotation of the strain ellipsoid relative to the stress ellipsoid, and structures cannot be used directly to retrieve stress. We try, but it's difficult. So you have different type of structures, schistosity that appears in the axial plane of folds. These schistosities are usually transposed in other schistosities. You have complex polyphase folding and the superposition of structures. So that was very brief introduction to structural geology, but just to give you a sense of the complexity and why it was neglected, this part, because it's not following the rules of continuum mechanics. Deformation is not infinitesimal, is not instantaneous, and it's probably not pure shear. So all these were defined to decipher the structures in the upper crust, and all these do not work in the lower crust. So how are we going to do? Because we want to move and improve the structural analysis of these rocks. Well, maybe the next step, I was asked that yesterday, I think, maybe, I'm not sure who asked me that. No, you asked me about the field of structural analysis, where it's going. I think so structural analysis really relied on continuum mechanics. The next step would go, if we want to understand structures in this type of rocks, that were probably two-phase rocks with liquid and solid, we need to move to fluid dynamics. And probably in these rocks, we can probably find structures that record laminar flow, turbulent flow, and so on. Fluid dynamics, not continuum mechanics with infinitesimal deformation. We're not there yet. So my first contribution to that, we were several researchers working on that during the 90s and 2000, was to look at the mineralogical composition, texture, distribution, proportion of granite and gneiss, and looking at the structures, measuring all sorts of things, and proportions between granite and gneiss. That's very important. And in order to improve, what I did is I read a lot on geometry of melt solid system, rheology of partially molten rocks and magmas, experimental work, conceptual work, theoretical work, melt crystal segregation, partial melting, fractional crystallization, melt magma migration, and metasomatism. So that fed my brain to then be able to find things that could relate to all these processes in the structures. So the geometry of two-phase system. So in the following, I represent the gray represents the gneiss, and the yellow the silicate melt. So that's conceptual. So at first, the first melt drops will occur between grains and be isolated from each other. So if they are isolated at the grain scale, they cannot connect, they cannot migrate. So at this scale, grain scale, the system is closed. All the melt is preserved in the rock. And as melting proceeds, the volume of melt increases, and at some point, the melt will connect. The small pockets will connect to each other, which controls the ability to migrate from one place to the other at the grain scale. So that's what's called liquid connectivity. It's the first percolation threshold. A percolation threshold is used in any type of science, not only geology. And then if the melt increases in volume, there is a second percolation threshold, which corresponds to the solid continuity. Believe me or not, but in the 90s, structural geologists started in 2 dimensions. They looked at that in 2 dimensions, not looking at the top of that diagram, and they identified only one threshold. Because in 2 dimensions, it's either the solid is connected or the liquid is connected. Structural geologists. And geologists are not good at physics. So at first, they started like that. So they managed to distinguish only 2 types of migmatites. Or actually, migmatites and granite. But in 3 dimensions, I can have my left hand with fingers connected. That might be the liquid. But the solid still connected around. That is my right hand. And at some point, the solid might disconnect, and that's the second threshold, whereby solids are floating in a liquid. And this is, so that's locked melt migration at this scale, at grain scale, and this corresponds to the transition from partially molten rocks to magma. And in magma, the solid might settle in the liquid. So it's a different process of melt crystal segregation than percolation through grains. And these thresholds might, if the magma has been separated from the solid, or at least partially, then the magma might take place somewhere else, and this threshold will be crossed in the way back during cooling and crystallization. So at some point, some crystals might be separate to each other in the magma during the initial step of fractional crystallization, and then the crystals might start to touch, form a continuous solid framework, but the liquid might still migrate through this framework. And at some point, the framework will be so dense that the liquid will be trapped in small pockets. And that's the final texture of the granite that I showed you with feldspars plagioclase, and quartz. The last melt drop is composed of quartz. So what is controlling melt migration? The geometric condition first is what is called the dihedral angle, which is the angle at the interface between the liquid and the crystals. And it's thermodynamically determined by the tension force. If you look at your water in a glass, if you look at the interface between water and glass, you see that there is an angle. It's not the intersection is not 90 degrees. It's an angle. And it happens that for minerals of the continental crust, for felsic rocks, the dihedral angle is below 60 degrees, which allows the melt to be connected for a small amount of melt. If it had been greater than 60 degrees, then the first melt pocket would have this shape, and it would require a lot of melt before connection. So in practice, for about 10% of melt in partially molten rocks of felsic composition, this connectivity is reached. So only 10%, 5 to 10%. For on the other side, crystal aggregation is also controlled by the geometry, the shape of the crystals, and the more compact they are, the more crystals is needed to ensure a connectivity between them. If they are very elongated compared to their thickness, then they might contact for low crystalline proportion, right? So it's the same. What are the driving force for melt crystal segregation? Well, the first one is viscosity. The viscosity is the ability of material to deform under stress. And the liquid has a low viscosity compared to the solid, so will tend to migrate into dilatant spot where there is decompression, and that's related usually in the rocks to deformation. So where the rocks will dilate, the liquid will go into it. The other force that we can invoke is buoyancy, related to density inverted gradient. And usually a liquid, well, it's not true in all conditions, but usually at crustal conditions, the liquid is less than the solid that it comes from. So they tend to segregate by buoyancy. But if we are sitting here on top of the Deccan Trap, or close, right? Deccan Trap is made of basalt. Yeah? Basalt, what controlled its emplacement on top of the Indian continental crust, do you think? Viscosity or buoyancy? Basalt is more dense than granite, even when it's liquid. So it's viscosity. It's the weight of the Indian craton that pushed on the magma that was produced underneath, and when it cracked, the liquid went up. Just by viscosity, not by buoyancy. Surprising, no? So melt migration, we saw percolation, that's migration of liquid across grains that are forming a continuous solid network. But there's also the possibility of fracturing, rupture. It's usually when there is a strong thermal contrast between the melt and its host rock. So it's not happening usually at the place where melting occurs. Segregation by percolation is happening probably at the place of melting. And then there is also the in-mass motion of magma by diapirism, which is driven by gravitational instability. And the crystals might accumulate in the magma. So all these are the processes and forces that can control melt solid segregation. The density of melt and rocks when they have been separated to each other. So if we take here the density and the melt percentage from 0 to 100% melt, what happens? So I represent here the liquid connectivity below 10% of melt. The solid continuity, according to the different geometric possibilities that controls this continuity, is probably between 20 and 60% of melt. Usually we take 40% as being a good average, but it's very heterogeneous. So if we take the density of a gneiss, it's usually here. Amphibolite is a bit higher density. A gneiss made of quartz and feldspar, it's here. And the melt, granitic melt, is on this side. So it spreads over a wide range according to its composition, but it's usually less dense, not that much, but less dense than the gneiss. So what happens at the liquid connectivity when the liquid segregates from the gneiss? Well, the residual solid will be, so the liquid will go, its density will resemble this one. And if it's extracted, then the residual gneiss will increase its density. And if you think about it, if segregation at this stage is efficient, well, the Migmatite should never have more than 10% of glucosome, which is not what we observe. So what we observe in the field is that sometimes Migmatites have more than 10% of glucosome. So that means that this drainage was not very efficient. So it allowed the melt volume to increase, reaching the solid continuity threshold. At this stage, its segregation will occur by accumulation of crystals in the magma, and the residual accumulated solid would have a density that is greater than the liquid. So you see that melt solid segregation will increase the difference in density between melt and crystals. So now in terms of rheology, so here we represent the strength of the rock in megapascals, and same here as a function of percentage of melt, with the same threshold, liquid conductivity, solid continuity. And what experimental work shows is that for rocks that have not too much melt or no melt, they are very resistant, and as soon as there is a few percent of melt, there is a decrease in 1 or 2 orders of magnitude in the strength of the rock. So the presence of melt will weaken the rocks. And then there is a catastrophic drop of strength by 4, 5, 6 orders of magnitude at the transition from partially molten rocks to magmas. But this is a log scale. So the first 2 orders of magnitude are very important. These look in log scale much more important, but you go from here to 100,000 to 10,000. So that's a lot. And this is represented in the few next slides in different scale, but here we can see that there are 2 thresholds. The first one is decrease in viscosity at the solid partially molten transition, and that probably leads to crustal scale strain partitioning, localization of deformation into weak zones. And within partially molten rocks at the contact of magmas, then there is another loss of strength that might be controlling gravitational instabilities within partially molten layers. And we come back to that later. So that's another representation of that thing, but in a linear scale. So in linear scale, the first drop is here, and the second drop is here, but it's not even seen at this scale, because it goes from 1 to 0.1. So you have to take a loop there, and in order to see that second threshold. So you see first one and then another one. So that's just playing with the scales, actually. Yeah? It doesn't show the same thing if you look at the log scale and if you look at linear scale. But I'm not going to go through that much more. Just remember that the presence of melt will weaken the rocks, and if the transition from partially molten rocks to magma is also associated with more weakening. Are you okay so far? I didn't ask actually if you had questions relative to yesterday. Now break?
No, we can take them in the break. We have about 10 minutes.
Okay. So now, metatextile diatextile transition. So that's now we're getting into analysis of structures in migmatites. So I thought, looking at the diversity of terms defined by Menert and the others, maybe what is really important is leucosome, mesosome, and look at the relationship, geometric relationship. And this allowed to distinguish between two different types of migmatites, the metatexites and the diatexites. That's much more simple, no? Rather than to have 15 terms, 2 terms, metatexite on one side, diatexite. The metatexite defined by a continuous gneissic foliation, which is marked by alternation of mesosome, leucosome layers. And you see here in this example that there are 2 superimposed layering. You see that? Darker here, gray, more gray here. What might, and then, so that's the meter scale. I lost the scale here, but there was a notebook somewhere here. That's something like 1 meter scale. And then within the darker, there are alternation between leucosome, mesosome, at a 10 centimeter to centimeter scale. Within the gray, there's also leucosome, mesosome, second order layering. What might these represent?
Segregation of minerals.
Yeah? Which one? Which layering what represents that?
So the white bands are
Yes, the leucosome, mesosome. Huh? I think that's my interpretation. Huh? What might represent the other layering at the middle scale? This might be a inherited banding from the photolith. Maybe more quartz-rich sediments and more clay-rich, mica-rich sediments. Metapilite, metagowaki. And both of them would melt, and you have a superimposed layering on top of that photolith layering. So that's one way to retrieve 2 different information, the history of the rock before melting and the history of the rock at the time of melting. But again, what I just said is interpretation, but you rely on the description of rock. You have banding at the meter scale and then layering at the centimeter to 10 centimeter scale of leucosome, mesosome. Make your description correctly before the interpretation. So that's an example of that. That's my PhD thesis field area. And you see here the continuous, or more or less continuous gneissic framework, and the foliation that is defined here as the syn-migmatitic foliation marked by leucosome, mesosome alternation. And you see locally, this leucosome is concordant to the foliation, and it shows also in the mountains. That's one of my best pictures. So I was taking the picture like we used to do, you geologists. We look at rocks like this, take pictures, and all of a sudden I had some wind, and boom, I saw the mountains. I said, wow, I see the structures in the mountains. And this made the cover of Terra Nova. I was presenting that at the oral presentation, and the editor of Terra Nova was in the room. I said, I want that picture for the cover of Terra Nova. He didn't care about the paper. He said, but I want that picture. Okay. And see that locally, the leucosome that is concordant here, up, is discordant. And my interpretation is that here you have a dilational zone that corresponds to boudinage, stretching of the gneissic foliation, that opens a dilatant spot into the melt, which will control the migration of the melt into it. And you see also a fringe of darker minerals, that's the mesosome, the melanosome around the leucosome. And that most probably reflects back reactions, retrogression, at the time of leucosome crystallization or melt crystallization. It will release water and will promote reaction in the host rock. So that's really, I think, telling us that this melt has crystallized and was produced here. It didn't come, it was not intrusive from very far. Diatexite, made of granite with very heterogeneous texture, full of enclaves of different sorts. You still see sort of a preferred orientation that might reflect orientation of solid bodies in the magma at the time of magma flow. So technically, this corresponds to a granite. No, most people would call that a granite. And you cannot blame them from that. But here, with the heterogeneity of and the richness in enclaves, I think it's more pertinent to talk about the diatexite, which is really part of the Migmatites, because it probably reflects the fact, and we'll see that with field examples, that this magma didn't move very much from its source. So it's really the field scale relationship that tells you if you should call that a granite or a diatexite. And we see that in examples. And that's here for the same field area. The first picture was taken, this picture is taken to the left of this one. And here we have the metatexite, ditexite transition, and it's made of a place where you see very complex structures. So it's the partly molten rock magma transition here. And we see that relationship between metatexite.
Those small enclaves there, are those garnets?
There are garnets, not probably in here, yes. Yeah, you see garnet in these rocks here. These are mostly metapelites, and you see, you can see the full metamorphic gradient, and that's a very good argument for also for having these rocks not be moved too much if they are preserved into their metamorphic gradient. And you can map in this region all the azograds from biotite, chloride biotite, and then garnet, and then staurolite, and then sillimanite, and then sillimanite with glucosome. That's also very important evidence.
In which of these types you will find pigmatic folding?
Pigmatic folding, probably in these ones. Yeah, there's been much. Pigmatic folding, I think, will tell you about the contrast in viscosity between the glucosome and the mesosome, and probably also it's controlled by the thickness of the glucosome compared to the thickness of the mesosome. Okay, so now that's the first order structural evidence. So now how it looks in microstructures. And that was even more difficult to address because, well, when we do experiment, you can quench the experimental molten rock, and then the melt will transform into glass. But first, these rocks were probably exhumed for more than 15 kilometers depth, 20 kilometers depth to the surface, and it took several million years. So this glass is no longer there. It's crystallized into quartz, feldspar. So it's difficult to distinguish because you don't see the glass. But still, if you look at it carefully, you start to find these textures, and especially the dihedral angle that is below 60 degrees, that is identified here in experimental work. You find them here. That's an example of interstitial feldspar in the quartzite, and you see these textures, they look very similar to that. So here we can propose that the feldspar was crystallized from a melt into a quartz-rich rock. Because rocks that are metamorphic and coming from more than 20 kilometers depth, usually the texture, microstructure, looks like that, with angles between here quartz crystals at 120 degrees that reflects reequilibration according to the tension force, at the surface tension force. That's like a tension force. Everybody's familiar with that? If you take a soap bubble, its shape is spheric. If you put bubbles together, they start to agglomerate, and the shape will be, if you make a section to it, it will be hexagonal. That's this shape. And that's controlled by the tension force, surface tension force. Yeah? So the driving force here, so that means that these quartz that probably started being sandstone. So in the sandstones, the quartz grains were rounded. So the quartz grain boundary migrated under that force, that tension force. So these are not fractures, these are grain boundaries. Okay? So this is true for quartz. It's true also for amphibole. Amphibole, that's not its euhedral, it's not its crystallographic shape. This is controlled by the tension force. And if you take plagioclase and amphibole, same, in the interface between these crystals, you will end up with, if it's been deformed under high temperature, we'll end up with a texture like this with 120 degrees grain boundaries. So, to find textures that preserve the melt crystals coexistence, you need to really seek for it. This is a very good example where you have a K-feldspar film around plagioclase and quartz. So most obviously this crystallized from a melt. And in other places you have these 120 degrees angles that are preserved. Same here with microclean, making a film around biotite, quartz, K-feldspar. So that most probably also was a melt film that crystallized, and it's been preserved. It's not been recrystallized. Another example with quartz. And here it's interesting because you have quartz and plagioclase. What might be the status of this plagioclase? It looks fairly euhedral. So my interpretation would be to say that also this plagioclase crystallized from the melt with the quartz. And probably this plagioclase might be residual from the rock that was molten. So then we start to point out, in these complex textures, which crystals are residual from the melting reaction, that were the reactant, and which minerals crystallized from the melt. And it's not obvious, If we look at that macroscopically, it's difficult to distinguish between this plagioclase and this plagioclase. And actually, I probably made a big mistake. I tricked you, but I'm going to suicide myself structurally. I think this was a big mistake. It was useful, but I took that criteria, and luckily I took a criteria that is objective in the field, continuity of the foliation, discontinuity of foliation, to distinguish between partially molten rocks, metatic sites, and magmas, diatic sites. I should say that, but I'm going to say it because I'm a honest person. By saying that, you say that all these rocks came from a magma. And this, for the Velay dome in the French Massif Central I showed you yesterday, it's 100 kilometers, so it's 3 times the thickness of the crust. So I said it's a crustal scale process. The implication of that would be that probably half of the crust was magma. We haven't identified that with geophysics. So I probably made a mistake by calling that diatic site to granite. So coming back to what I just showed you, how much is this plagioclase and feldspar residual from the previous rock, the reactant of the rock that was undergoing partial melting? How much of this plagioclase, probably K-feldspar, crystallized from a melt? Probably not 100%. Probably half of it is residual. And that's the field of research I'm investigating now, is looking at these rocks, trying to identify texturally, chemically, crystallographically, which one are the reactant, which one are the product of the crystallization of the melt, which one are also, there are also other crystals that do not talk, this is probably more for the master students, the peritectic minerals. The one that crystallized with reacted, that are the product of reaction with the melt. But they never been crystallized from the melt. They are solid. So that's the next step. But let's continue. So these films might also form what we call granophyre or myrmekite, which are really intergrown K-feldspar and quartz for the granophyre, pleasure clays and quartz from the myrmekite. It's difficult from the eye, even with a microscope, to distinguish the two. Other type of migmatite, myrmekite or granophyre, forming films around crystals. Same. So let's move back now to the macroscopic scale. So these textures, and here you see the garnet, and around garnet you see the leucosome. This was also my field again for the PhD, and I was very pleased to see limonite that big. Didn't need a hand lens to see them, because I'm not a very good petrologist, so I'm happy when the minerals are big like this. And here you can see that it looks like an eye. So the garnet is surrounded by leucosome. So that's a good evidence, I think, to call upon a peritectic garnet that was formed as a reaction, as a produce of melting reaction with the melt. So here in that, this is all the result, that was the product of the melting reaction, but only the quartz and feldspar, and probably not all of it, crystallized from the liquid, and this was a solid product. And you see that here, this underlines the foliation. So this process that occurred at the grain scale is already the result of segregation of all the liquids forming at the grain scales to form these leucosomes. That corresponds to the first migration by percolation. In other words, this didn't form here. This melt didn't form here. It formed in this rock and was collected at the grain scale by percolation during deformation. So this foliation is not inherited from the protolith. This foliation is recording the process of deformation during melt segregation at the grain scale. So the semi-migmatic foliation reflects melt segregation coeval with deformation. Melt might also migrate into budins. When you have more resistant layers, they might localize deformation, whereas the other ones that are weaker will be continuously deformed, and these spots will drive melt segregation.
Is it okay to call it a budin?
Yeah? No? Yeah, budin? No? The definition of budin is that you have initially continuous layer that is stretched into several parts.
So you can call it a budin.
I think so. Yeah. I mean that's what I do in the field. You have here leucosomes that are both folded and also in the axial plane of folds. Another structural sites of melt segregation. See here a series of pictures of leucosome, mesosome, and a small rim of melanosome. And that reflects also probably, and you see there's some sort of repetition between leucosome, mesosome, and that's something that probably tells us something about the physical process. Say another example. So I'll skip that. And you say, Malika, I should almost close, huh? Okay. So, yeah, we used the asymmetric distribution of leucosome relative to the gneiss to infer polarity of melt segregation, melt migration. And I think what works very well is, you see here there's the leucosome, the same here, leucosome, and here budinaged layer that is more competent, and you don't see leucosome on the other side. So there's leucosome only on one side. And this we interpreted as, that was my master degree, interpreted as being related to migration of melt that was stopped beneath a mechanical barrier. And that, in other words, will be used to tell the polarity of migration. And it was funny because at the time, everybody thought that granite melt would move upward. But when we said this is a polarity structure, I said, wow, how do you know? I don't know. But I could find that this distribution of asymmetric distribution of glucosome relative to gneiss is consistent at the regional scale, and it's always gives the same polarity. So I think it was very compelling. Another type of polarity structures, these what we call cauliflowers. You see one side of the glucosome vein is fairly straight, parallel to the foliation, and the other side is sort of rounded and is discordant on the foliation. And we took that as being evidence of small diapias. It also tells you the polarity. So we saw melt segregation to form concordant veins at the grain scale, but then these concordant veins might connect to discordant ones. As very often as we see that. Well, basic structural geology will tell you that this cross-cutting is later than this. But the textural continuity of the leucosome from here to there, I think I would interpret that to be magma at the same time, and then crystallize from the same magma. And actually here you see a diffuse relationship between the leucosome and the mesosome, whereas here we have a more quartz-rich rock, then here it's very sharp. This is intrusive. This is not intrusive. This is extraction. And you see the cordiorite, that's not garnet, that's cordiorite. Cordiorite is found in leucosome concordant and also in the discordant ones. So it's another evidence for having the same melt being concordant to the foliation discordant. So this also is contemporaneous with deformation and opening of dilation sites. And usually concordant leucosomes are found for less than 20% of leucosome in a rock, and as soon as you reach more than 20% of leucosome, then you have this concordant-discordant relationship. So another place where it was wonderful to study this transition from metatexite, continuous framework with concordant and discordant veins, to diatexite, enclaves into heterogeneous granite, is Namibia. And here it was very compelling to see that metatexites are always on top of diatexites that are diatexites in the core of large-scale domes. So I think this also gives us a continuity and the increase of amount of melt. Maybe not partially molten to magma, but increase of amount of melt going downwards in structural section. And for the, I mentioned the diapias. It was not very famous, popular. In the 90s, people thought, okay, diapias, that's old geology, doesn't work. In the field, the melt only migrates through dikes. Well, here I had one of my geological ecstasy, and we were walking along a trail, and we saw that in two migmatites. You see the structure of migmatites like this, and you see it's going like that. And that's caused by more granitic rock. Well, I'm not sure if you see the same thing as I see, but these diapias, they tend to form mushroom shape. I see half a mushroom here, but I'm very fond of looking at mushroom in the forest myself when autumn comes in France. So I have the eye for mushrooms. So this is half of a mushroom. So diapias exist. Maybe not in the upper crust, but in mid to lower crust. Well, you find this not that often, but it's the more you look for it, you'll find them. Do I have time to do some physics? Short?
Maybe you take a break and come back.
It's not good, because that's after it has nothing to be related. So I'll be very short. So this might be represented by what is called the compaction theory. It's like if you take a sponge with water in it, if you push on the sponge, the liquid will segregate by percolation, and there is some kind of repetition or frequency of that compaction. It's called the compaction length, which is related to permeability and viscosity of matrix, viscosity of fluid. And it's been shown that it could be one way to explain this repetition of leucosome mesosome. And both for concordant and discordant ones, this is also kind of compaction theory. Veins might also form according to shear bands and localize also folds. So I'm not going to go through that further. We can build the same story for the crystallization. And if you have contacts between two different types of granite, for example, leucogranite and granite with phenocrysts, well, you see that here some of the phenocrysts are also, so the boundary is not like a sharp one, intrusive one. So most of the phenocrysts are here, but some are floating in the leucogranite. So I would take that as an evidence for accumulation of crystals rather than having two different granites. It's the same, but most of the crystals are here and the residual liquid is here. Of course, it will affect the chemistry because the minerals are different, but it doesn't mean that they were coming from a different magmas. It's the same magma. Same here. Same here with accumulation of garnet in the first part. That's Ukraine. Was in Ukraine in 2004 or 5. It was a time that Soviet Union, fell about 10 years before. It was kind of floaty. The ambience was floaty. This is close to. It's in Donbass, and uranium mines everywhere. So we'll talk about that on Thursday talk about social impacts and social challenges related to mineral resources. There's no surprise that the Russians went there first thing, right? And I'll leave you with questions. Here's an example, a fantastic outcrop with Migmatites, very heterogeneous, and you have here an enclave into a diatic site, and within that enclaves, different enclaves into enclaves. Wow, that means that's a very dynamic process. You had enclaves and then crystallize in some kind of a partially molten matrix, and then this enclave was then re-put into dynamics into a partially molten rock. So this means that these processes are very dynamic. Dikes in dikes, two dikes that are separate from each other, and then up, they become the same dike. We saw that yesterday with the DPEC, of multiple intrusions. So it's not always differentiation of the same magma. It might be one magma that comes into another one. Same here, up. And magma interactions, magma mingling between a mafic magma and a felsic magma. I think I'll stop with that. No, I'll skip the Pluton. I'll have a conclusion. Okay, that's my conclusion slide. So melting starts at the grain scale with small pockets, and probably where all the minerals that are required for the melting reactions are connected to each other. So in other words, K-feldspar, quartz, biotite, if you have biotite dehydration melting, and then will lead to formation of small melt pockets in between grains. When these are connected, they will feed. This will not be really identified at the microscopic scale. You need to go at the microscopic scale to see that. And the only evidence for melts, the presence of melts, is when you start to have melt segregated in leucosomes. So it's already 10% of melt. When it's less than 10%, you don't see it in the field. And then beyond 20% of melt of leucosome, you start to go from concordant to concordant-discordant veins. And that's probably the process that is required to have migration of melt out of the outcrop to feed plutons higher in the crust. And that's if the melt is well drained out of the rock. If it's not the case, then the melt will accumulate. We go beyond the metathexite, diathexite transition, and then you have accumulation of solids into the magma. And this will lead to crustal differentiation, so that was my mistake, magmatic zone here. Maybe I need to refine that. Accumulation zone at the bottom, partially molten zone, and intrusive zone that corresponds to the magma that has migrated out of its source and being intrusive in colder rocks. Okay, let's take a break. But you can ask questions if you have more now. Yes?